The following content has been provided by RWTH Aachen University.
Welcome everybody to Designing Interactive Systems 1. Before we get started, I wanted to do this quick announcement. Every first Friday of December each year, we celebrate the people who finish their degrees. Everybody gets their diploma, their bachelor or the master's diploma. We've got great food. We've got lots of companies who are really eager to hire you right off the spot for a job. This year, this happens online. Since we can't meet in person, we're doing this virtual event. So even if you're not, receiving your diploma yet, which probably most of you won't be because otherwise you wouldn't be in this class today, this is a great event to join because it'll give you a chance, an early chance, to check out companies in the area, across the regions from all of Germany, really, who are interested in hiring computer scientists, so you can check out the job market a bit. Secondly, you'll get a 2-minute madness kind of expo that shows you what current research is happening around the computer science department. So, from our lab, but also from many other labs, there'll be short videos of PhD students explaining what they're doing. And it's a great chance to see, what might tickle your interest, for example, for your thesis work. So if you want to join that, there's a registration you go to at tdi.ac, Tag der Informatik. It's free, of course, but you need to register so that you can join the online event. You don't have to then actually sit through all the different talks or presentations. There will be online rooms that you can join, and then there in that room you can pick any of the presentations. It's like a virtual theater hall, but you choose the program for yourself. You can also check out a short speech I've gave for the graduates this year that is mildly subversive in nature, and it should be a fun event. So I hope to join you, to see you guys there, and it'll give you a chance to talk to people from industry, talk to people from research labs, talk to each other, and see what's going on in the computer science department in general. So tdi.ac, just go there and sign up this Friday, starting at noon. Now on to the main class here today in Designing Interactive Systems 1. As I said very early on when we started this class, it consists of 3 parts, right? It consists of this part on basic human psychology. We've been through that. You guys should have read Norman's book by now. We're done with that section. We have the second part that is about the history of HCI, because like an architecture class, we're going to look at existing systems, if you want, the grandmasters of the past, to learn from that history and see where HCI is heading and how we got to what we're doing today. And this will not just be a look back, it'll also be sort of a look back and forward, because we'll take a look at some of the future vision videos from the past. That will be very interesting to see, because you can tell kind of what kind of things we've already, we've already fulfilled those visions and where we're still falling short, or where things have just gone completely different. And then the third part of the class will be this prototyping skills, evaluation skills, usability, engineering skills to help you run the process with a client, for example, to arrive at a great user interface. So in a way, the first part gave you the fundamental rules of human psychology that always apply, no matter what interface you're designing, what your task, what your context is. That second part gives you the intuition of where HCI is coming from and how we got to where we are today and what might be up next in the agenda on research. And then the third part of the class will give you the training to fine-tune an interface and to arrive at the right interface for the particular task and a particular user in a user-centered design fashion. Okay, so before we jump into that, let's do this last round of quick reviews on what we talked about last time, wrapping up the stuff that we discussed based on the book by Don Norman. So we actually, sorry, not Don Norman, but last week we were talking about visual design, which is not part of Don Norman. That's part of another book that I shared with you. There's Design for Non-Designers. And here we covered a few visual design principles. So Can we hear a few ideas on what are the 4 basic principles of visual design? They had a nice acronym, so that should be easy to remember. Bilit, go ahead.
It's PARC, proximity, alignment, repetition, and contrast.
Exactly. And if you take color, for example, how do you create contrast? How do you pick colors that create contrast while still working well together? What kind of tricks did we learn in that respect? See here, Aparna, go ahead.
We can basically form the Newton color circle, and we can pick the opposite colors, or we can also make it triangular and pick 3 colors, which would also contrast with one another. And one more thing I remember is you can pick 2 colors which are kind of nearby with one another and one completely contrasting. So that is also a possibility.
Exactly, where you go across the circle and then pick the 2 neighbors, basically.
Yes.
And then, of course, there are other ways of creating, just changing, for example, the saturation or the brightness of an individual color to arrive at more different variants. Great. And we talked about fonts as well. We went through a couple of different font types, fundamental types. Do you remember which ones these were? Starting out with the font discussion, we had a look at fundamental types or schools or classes, if you want, of fonts. I'm going to wait for another blue hand here, apart from Belit and Aparna. Or what's even more fun, I get to pick somebody at random. How about Anya Veliva? Anya Veliva, you are, your camera is off, your microphone is off, but I'm hoping that you are around. And let's hear if you can remember any of the basic font types.
I'm here, but I don't remember. I would have raised my hand up.
Okay, never mind. Anybody volunteering? Yes, there's a volunteer. Fabian, go ahead.
Yeah, there are 3 types with serifs. These are old style, which are like the closest resembling handwriting. So they have these 45 or 30 degree angle where the letters are also the thinnest. And they have these serifs guiding the user to read in the straight line along the letters. Modern is like a little bit less according to these handwritings. It doesn't have the 30 or 45 degree angle anymore, but it instead has the thinnest part on top of the letters and on the bottom. And it doesn't sometimes also doesn't have the transition between thin and thick anymore. So there was this example with the letter, the capital W, which had like a very thin line and then a very thick line right next to each other. And I don't really remember what it was called, but it was called something serif, which called it like it was like similar to sans serif, but with serifs. But it had like all the same line thickness in all types of the letters, but it still had serifs. And then there was sans serif, which didn't have these serifs anymore, which you could use for like lesser parts of text, where you wouldn't read like a whole block of text, where you wouldn't really need that guidance anymore. And then there were like 2 other classes, which were script and decorative. Script was like resembling handwriting in any other type, but not really good for reading it anymore. And decorative was like where someone definitely put too much consideration into how it looked like and didn't really think about how easy it was to read.
Right. So you want to go for, use those last two ones, like maybe for short amounts of text, and decorative maybe for like a single word or something in an advertisement, or if you want to evoke a certain strong association with a particular atmosphere, for example. One minor thing, you said initially the old style mostly resembled handwriting. You're right, if we refer to the handwriting of a pen with a nib in the old style, right? The modern handwriting is more closely resembled, of course, as you said, by these script types. And the one that you're missing, I think, is the one that was called slab serif, that had these over emphasized serifs at the edges of letters. Right. Okay. And you already explained what, when you would use serif, not probably for your basic, when you would use serif typically for your basic text because it's the most readable one. I think that's just something to keep in mind, especially now that we've got basically displays that rival the resolution of print and laser printer pages. So we no longer have to think hard about low resolution. Although as soon as you end up in, like, for example, an industrial display that has a low DPI pixel count, you may end up having to rethink all this and go back to a more appropriate style for very low resolution. And there are special fonts, of course, for that you probably still know from your 80s retro video games. Okay, another one that I just want to make sure that you guys have some of these things as intuitions in mind whenever you design presentations, text layouts. What's the maximum text line width for a well-spaced text, where the lines are far enough apart from each other? How many characters should you put per line? So you're a very simple thing. You're laying out a page with text. You have an option to go for 1 column or 2 column or 3 column maybe. One of the things that should drive your decision there is the line width based on font size, of course. You get more or fewer characters per line into each line of your text. What's the number where you should roughly end up to make sure that people can skip from the end of the line to the next one? Yeah, Ezra, go ahead.
I'm not sure, but I think it was fewer than 60 characters.
60 is a good rule of thumb, actually, to keep in mind. So up to 60. Beyond that, things get a little harder to read because you have to go back quite far to find the next line, and on that travel back, your eye may lose the correct line. You will find, if you take, for example, a small print full width A4 sheet, it's actually not that easy unless there's a lot of line spacing from one line to the next to read these lines continuously, especially if they're all right adjusted as well, because then you don't have this optical cue of, oh, that was a short line, that was a long line, right? They all look the same from that point of view. Okay. So to start off with today's topic, I'm going to jump in and show you a radically new interface. This is a watch designed by Casio. It's a pretty cool one, the AT550. What it actually lets you do is, it's a calculator watch, but it's not your average calculator watch, the one with the tiny buttons on them, which are kind of dorky. It actually uses a touchscreen interface. And not a touch screen that displays things. As you can see, it uses a normal LCD and analog display underneath, but the touch screen is actually just a touch layer on the surface glass here. So it's kind of like an Apple Watch touch input, but not using the display at the same area where the touch is, but just using the touch layer. And what you can do is you can actually enter numbers in calculator mode by simply drawing them on the display. And since numbers are, there's only 10 digits and a few symbols like equal and times and plus and minus and so on, it actually does a really good job at distinguishing these. And you don't even need to look at your at the watch, so it has an ice-free operation too, right? You can just do that without really looking at it. So it's pretty cool. There's only one minor snag with this. If you're like, I might find that interesting, you know, for Christmas. This watch was unfortunately released in 1984. So what I'm trying to show you with this is that new ideas like, you know, touch input, for example, are not things that happen in one sudden gap. It's not like somebody sat down at Apple and one day said, let's do an iPhone and this is what it looks like. And that was like the first device ever to look like this. All these things actually take many, many rounds of try and error until they finally break through into the main market. This was shown by Bill Buxton, a researcher from Microsoft, at CHI 2011. He had a whole exhibition. He has a collection that you can actually check out online at this URL there at the bottom, the Bill Buxton collection of user interfaces. Really interesting stuff. He's a very well-known HCI researcher, and he has also a couple other great examples. For example, there's a phone that looks just like an iPhone, and it was, you know, it's a touch screen. It's got little icons for input, like a you know, a splash, like a home screen on your iPhone. And it's from IBM. It's called Simon, and it's also from the 1980s. So there's this no single hero principle, as Buxton calls it. Even an interface that may seem radically new, like maybe the iPhone, was actually built on lots and lots and lots of previous iterations, right? That's true for touchscreens. It's true for the mouse. We have seen the original mouse, or we're going to see a video on that actually today, that was developed by Engelbart, but even he was building on a lot of existing research on other input devices, right? So things evolve over time. Technology is just like culture, right? It evolves over time, and many times you can actually see shades of the past in present technologies, like, you know, in the iPhone you can see lots of things. Johnny Ive was very clear that the way that he designed the original white iPod that you may remember was fully based on the design of you know, radios by Dieter Rams from Brown from the 50s, who was like a design icon and a design hero in those days. So people are stealing ideas. They're building on what's out there already. Of course they are. And so it's an iterative process, right? It's not somebody sitting there suddenly saying, oh, let's do this as the iPhone. Or as Bill Buxton put it when he gave a talk at CHI that year, he said, you know, Picasso, who everybody, you know, celebrates as this, you know, completely rule-breaking revolutionary artist, he knew everything about art history because, you know, he had to kind of know the rules before he could go ahead and break them. So it's nice to invent new stuff, but it's pretty helpful to know what's already out there, right? Don't reinvent the wheel. You may very well come up with a cool idea, but it was actually already tested and with users and it failed horribly. And then you need to go back and find out, why did it fail? Maybe technology has moved on since and you can try again with a different approach. Or maybe it's really a bad idea and it's not worth spending that much time on it. So with that in mind, let's do a quick review of the history of mankind under the light of HCI, okay? We're going to jump into the pre-computing phase, and we're going to start with things like the abacus. It's always interesting to see, do we have anybody here today, can you raise your blue hand, if you've actually used an abacus at some point? Okay, Tejasvini knows it, Sven knows it, Marta knows it. Wow, that's a lot of people. I'm surprised. Good. All right. So the abacus is like really old, right? It's 2,000 years before Christ. And what I find interesting about it, when you think about it from an HCI perspective, is yes, it's the first, you know, known mechanical calculating aid, sure, but it actually does not have a user interface, right? The thing is the UI. There is no hidden layer of mechanics, you know, and certainly not software, obviously, that you cannot see. what you're interacting with is everything that's there. Right? There's nothing hidden. So the system is the UI, and that's actually a wonderful place to be because you don't have to hide anything behind a veil of user interface that you create. It's just very raw and transparent and one-on-one. But we're not going to get back into that ever again, basically, after this Abacus, at least not with computing technology, because after this, things started to become more complex. And immediately people started realizing, whoa, that complexity, we need to provide an interface to that so that people can actually use it. Not everybody who uses a calculator needs to understand how it works, right? So take Da Vinci's mechanical calculator designs from the 1500s. They are pretty complex. But as you can see here at the back here, there is a lot of mechanics going on, but the front actually has a few wheels that you can set numbers on and operations on. So it already creates this front end or user interface and internal working distinction. So we're beginning to see the concept of UI in these apparatus. Then if you look just a little further, we've got, like Pascal's arithmetic machine, for example, here by Blaise Pascal. And that already had, fundamental operations on here. That was the first one that actually worked, right? Da Vinci was a little bit ahead of his time. People couldn't mechanically make the things using the tools of the time that he was dreaming up. But Pascal's system, that was very similar to Leibniz's machines or the machines by Chicard. That was the one that was the first working model of such a calculator, and that and could do things like additions and subtractions. So we do have certainly a user interface component here, because now you can see actually now it's hidden in a box, right? It's inside a box, and there's something on top of that box that is creating a UI. I just want to check, Yuru, you got your hand up. Is there something you wanted to add? Or is that just a leftover blue hand? All right. The driving force behind these pre-computing systems was basically, when you think about it, we're moving from a direct representation of the conceptual model, like with the Abacus, to more and more increasing levels of abstraction that need to then basically the abstraction is given to you in the user interface, and the complex inner workings are not something you need to worry about. Okay. So let's move on to the first computers. The first computers were built around the 40s, ENIAC as part of the, developed during the war. And they had a very interesting way to program them. We can actually see a later version of that here on the right-hand side, an IBM version. The ENIAC is the one on the left here. This is, the interesting thing is these things didn't actually have memory to store programs. There's no memory to store programs. You're actually plugging cables in to make these computers do certain things. Basically, your program was being represented by a bunch of cables. And this is an interesting technique if you think about it, because the code, the coding, the programming happens very, very clearly right in front of you. But we quickly moved away from this architecture, and von Neumann, the guy that you saw in the last picture, he was standing in front of ENIAC, which is kind of funny because he was basically standing in front of the computer that he would make obsolete with his inventions. The von Neumann architecture actually is the one that we are pretty much using to this very day for our computers, right? And you've all seen this in your basic computer science classes. So you got your CPU with the control and the arithmetic logic unit. It talks to memory, and then it has external storage, and it has input and output devices. So Neumann's key idea was to store not just data in memory, but also store the program instructions in memory, right? So that's moving the program from being plugged and hard-coded, literally, very hard-coded, to being part of the code that's stored in memory. That was the key idea. And back when von Neumann created this architecture, it also made a lot of sense because The CPU, if you look at it here, is at the center of everything, and everything else is kind of attached to that. And CPU time was very expensive back then. And if you wonder, okay, what about user interface? It's interesting because essentially von Neumann was aware that you needed input and output on the computer. There would be a UI, but he didn't think of it as a component was specific to user input. He basically just said there's going to be input devices and output devices, and whether that's, you know, a printer printing stuff out, or whether it's a screen showing stuff, or whether it's a file we're sending things to, he basically considered all these output devices, right? And input devices could also be, you know, a keyboard, but it could also be something like a data read in from a punch card. So that means input and output was really not considered, or the user interface was not considered separate from all the other technical input and output that was going on in the computer. The UI, what users were creating, was just another variant of input to a program's instructions and running. And that's actually something that stays with us for quite some time. This setup, by the way, is similar to Konrad Zuse's design, our European pioneer, if you want, who created the Z1s and up to the Z4s at the same time. So as we move on into sort of the 60s and 70s, we saw the arrival of mainframes. These systems were using the concept of batch processing, right? Which basically means that the program would require that its data was available as input at the beginning. When it starts running, it reads in the data, processes it, and then spits out the result, right? On usually maybe a typewriter output, or early on you would get input and output on punch cards. Punch cards were an interesting technique. Has anybody held a punch card in their hand, actually? Yes, okay. Okay, Annika, why on earth have you held a punch card in your hand?
I don't know if it counts, but it was in the Kommunikationsmuseum in Aachen. Ah,
okay.
So, yeah, they had some there.
Excellent. Okay, so yeah, so basically, you punch little holes in there in these rows, and that would mark what kind of data you were supplying. This introduces a particular way to work with the system, right? You prepare all your data on punch cards, you submit a stack of punch cards to the operator, and that would contain your data, also your program, and then it would run, and the next day you would come back and pick up your printout, and hopefully everything worked out fine, or maybe you made a mistake on your first card, and then it wouldn't run, and you would have to basically another day of doing your punch cards. And you certainly didn't want to drop your stack of punch cards back then, because that was a big mess. This is also technically driven, right? I mean, user interface and technological development always go hand in hand. What was the reason why things were designed that way? Well, because the machines were really, really, really expensive back then, right? So compute time on the CPU running your job was extremely expensive. That's why it was perfectly fine to have a human labor away creating these punch cards for days and then run it into the computer, because running that computer and running the program was incredibly expensive, because these things were slow. They took a lot of maintenance, stuff kept breaking. So it was an efficient use of the machine. It didn't have to wait for human input because it was already supplied. Nielsen, Jacob Nielsen is one of the key sort of design advocates for the web since the 90s. And he calls this an excellent book, Usability Engineering, which gives you a very nice hands-on way of introducing usability into companies. So if that's your thing, that's a great book to pick up. He calls this a zero-dimensional user interface. He says zero-dimensional because interaction basically happens in one point in time, right? There's only one point in time where interaction happens, where you give your data to the computer and then it takes off and does its thing. Writing software is actually fairly straightforward this way, right? You don't have to have a a loop in your code that keeps looking for new user input that might be surprising and different from what you had before, you know that all the data is provided to you at the beginning, and you can work with it at, put it into an array and use it in whatever way you want. So there's certainly, this is not something where you would talk about real-time feedback, right? On the bottom, by the way, you can see a machine for punching these cards. And interestingly, the people who were operating these machines were called computers, and it was mostly women doing this job. All right, so then next up, transaction systems. As an example here, the Sabre system or the IBM 3270 from the 70s. These were not general purpose computing systems. They were still specialized systems. In these cases, we were basically moving slowly from this punch card input to now having an electronic way to input your data. So you had a very, very simple terminal. These these systems, these special purpose systems would allow you to timeshare, right? So now you had an option to actually get immediate responses for lots of users from distant terminals, but only for special purpose applications, right? So maybe just for running, let's say, text calculations or something like this. So timesharing is the sort of, the architectural software concept behind this. And timesharing, of course, then continued to become more and more common and actually ultimately made its way into general purpose operating systems, right? And this is where you might be starting to see things that are familiar to you. Not this teletype, of course, this machine here, but the concepts behind it. Because timesharing operating systems allow general purpose applications that gave interactive response, so immediate response, efficiently to a lot of people simultaneously with one computer. Because remember, computers were still the expensive thing, right? Not like today, where the user's time is usually much more valuable than the computer hardware cost. This is when we arrive basically at things like MIT's CTSS and ITS and ultimately Unix operating systems. Originally, these were operated with teletype terminals, so things that you would normally use to send data, like in telegrams across the country over wires. These were being reappropriated, if you want, for computer input. So you'd have a keyboard to type in your things that would get sent over this data line to the computer, and the output would come back on this little strip here with punched holes, right? That was kind of like Morse code, if you want. Later on, this was then becoming more interactive because the teletypes, the original ones, were then replaced with glass teletypes, which are essentially computer terminals, very stupid terminals. They only had an addressable character screen, so you could only write on individual characters, and the interface was still command line based, right? So this is where the interface of the command line concept was really taking off. And this move to these time-sharing systems, we could consider that like a 1D interface, Nielsen calls them, because now what you do is you have a string of characters that you type in, you send it to there's actually literally a send key on these things, right? That sends it down the line, and then the computer processes that input, processes the complete command that you triggered. It's a little routine, a little program. The program ends, it spits out some results. Those get printed on your printout, and you can see what's going on. Or later on, they would appear on your screen. But for example, there was no way to go 5 lines up on your screen to edit something that's up there. That was not the way that this worked, right? You entered things down here, sent them off like a telegram to the computer, and the computer would send back data to you, and it was just being displayed on an endless scrolling page that was going up. And that is probably something that is still familiar to you, because if you've used any Unix command line interface on like a Linux box, or if you open the terminal tool on Mac OS X, you still get that exact same interface, right? In fact, we see a lot of these things still in today's systems, because if you take a look, for example, at how you connect with terminals, they still are called, serial connections. And these serial connections, the VT100, for example, is a standard that was actually based on an old glass teletype computer, right? That actually lasts on to this very day. And so these things are still in today's Linux and various Unix types operating systems. But the problem, of course, is you couldn't do a full screen editor with this, for example, right? There was no way to create a program that would let you edit things on the screen in a full screen way. That was not available yet. It was still this lines back and forth kind of thing. MIT, by the way, the systems developed there, the first one was like the concurrent time sharing system, compatible time sharing system. And then they created the ITS, the incompatible time sharing system. And then ultimately, Unix came around on that. If you've used command line tools, then you know that even today, when you type in a command, like for example, copy file A to from this folder to this other folder, then that is essentially providing all the data that you can provide right at when you run the program. Then a tiny little program runs. The copy command is a little program. It runs and the results get spit out on the screen for you, right? So you can still actually experience this 1D interface on today's terminals. Now, it's always interesting to see that there's the industrial development of things that are happening over time, and then we see at the same time people having crazy ideas that are way ahead of their time, and sometimes they get, ultimately reality catches up to that. Sometimes it doesn't. And Vannevar Bush's article from 1945, As We May Think, so the way that we may be thinking and working in the future, was one of those articles, probably one of the most well-known visionary articles of computing. It was kind of a sci-fi vision. He envisioned that, people would actually be interacting with information. Remember that 1945, there was no computer around, right? That didn't exist. ENIAC was just being invented. So it's at the end of the Second World War that we're talking about here. And we have a little video of this thing that I'll be showing you in a second. But the device that he invented or that he dreamed of, he didn't build it, right? He just sketched what it might look like, was called the MEMIX. And he had to go with what he knew, right? So it's based on essentially microfilm recordings of data, lots and lots and lots of data, and clever ways to look at that data and to sort through it and to search through it. So it's a device that stores everything of like, all your books, all your records, all your communications. He said those could all be in the MEMIX. It's like your personal information storage, basically, that has everything in there that you've ever taken a look at. And it was claiming that you could consult this information with exceeding speed and flexibility. What Bush actually predicted with this were not just the personal computer, because he was essentially describing something like the PC with, but without the technology around yet. But he also predicted the networking of these things, through the internet and the World Wide Web. He predicted hypertext. He said that would be links from one element in your MEMIX, from one book entry, for example, you would directly go to a reference that this book makes to another book. He was predicting speech recognition, that this thing would somehow recognize what you're saying and then go to the right page. It was predicting online encyclopedias like Wikipedia, essentially. So it was a very, very visionary article. So we're not making this a required reading, but I really recommend to take a look at this article. MEMIX, As We May Think, is the name of the article. So here's a short video that was produced much later, obviously, to illustrate sort of what the idea was that Bush was trying to express. So that's the MEMIX. As you can see, there were people out there that already had very far-reaching ideas, and it would take technology many years to catch up to that. Meanwhile, in the real world, we were still at things like Unix and fully text-based, full command line-based interfaces, right? And so then slowly we saw things evolve from that. Around the 60s, for special for special application areas like air defense, for example, the SAGE air defense system was a system that, as one of the first applications, actually pushed the idea of a real-time response system that was graphical in nature. Well, I'm hesitant to call it a GUI because it is really it's essentially a radar display, but it was able to show you flight paths and let you explore things on those flight paths in real time. SAGE stood for a semi-automatic ground environment. Basically, it took all the radars around the country, connected them via phone lines. That data went to a big computer, and that big computer then was hooked up to many of these CRTs that you can see here in this picture in the control center, and then the operator could actually see the data that was being collected. So we could call this maybe a graphical user interface, sort of. But the real breakthrough in graphical user interfaces hasn't happened yet, right? This was actually only happening with Sketchpad. Sketchpad was a system that Sutherland created in the 60s, and Ivan Sutherland really made a breakthrough development here as part of his PhD thesis at MIT. He created the first interactive computer graphics program. So this was the first time that you could do some general purpose graphical interaction with a computer, directly manipulate objects on the screen. It even included things like constraint satisfaction. So you could say, I want these lines to be at a rectangular angle. And it would basically resolve that to be true in your drawing. The video we're going to see was made by an MIT science reporter. So basically somebody who was in the PR department of MIT and who is basically playing dumb to ask the questions that the general audience would want to understand from this work. And we're going to see Sutherland being interviewed in this video. It's interesting to pay attention to the things that Sutherland does here. Pay attention to the applications that he can run on this thing, and also pay attention to the input devices that he uses, because they're actually quite unique. And finally, also try to find out in this video, what are the things that the computer enables you to do? What kind of intelligence does it have? What kind of concepts that maybe from today's graphics programs are actually being pioneered here, okay? So we're going to roll that video next. This was actually released as a as a historical review of at Chi in the 80s. All right. So I find these highly entertaining. So first of all, these people are wearing cool glasses, of course. That's one advantage we're getting here. But also, I think I mean, you look at this guy, he's sitting there talking about, next we're going to do handwriting recognition and speech recognition, something we're still kind of, just getting to really deploy today. And he's sitting right next to like a freaking old school, black dialing wall phone, right, in the 60s. So what this really illustrates is that there is this really long phase between when people first have an idea, and that idea keeps getting worked on, keeps getting rethought, keeps getting tossed around, applied, changed, modified, until it actually gets into being deployed. This can take easily 30 years and more, as we can see from these examples. What you should take away from this video is, first of all, the input technologies. As I said, there was a light pen that would let you directly manipulate objects on the screen, something we haven't seen before. And if you want to download you can download the PhD thesis from Ivan Sutherland. He wasn't in this video, unfortunately. This was his colleagues. But if you look at his PhD thesis, he actually has like a little technical electrical explanation drawing that tells you how the light pen was constructed that he used. He then has shown like separate physical buttons for control, right? There was an individual button for each function to press on that field. There were also dials. I'm not sure whether you noticed this, but at some point he was actually able to, you know, pick an object, move it with the light pen from left to right, and at the same time rotate it by turning a dial. Try that in Illustrator today. You'll be struggling, right? Because we don't actually have these, you know, bimanual complex interactions quite as flexible even today. So scaling and rotating at the same time, for example, or moving and rotating, those are interesting combinations of things that we could see in this early example from the 60s. We saw that he was able to create not just copies of objects, which is easy, but actually references, right? You know, links to objects, so that there was a master copy, and if you changed that, then everywhere it appeared, it would change. We saw hidden line algorithms. You could sketch in 3D. You could do even graphical flowchart programming, right? So you basically create you draw, you sketch a running flowchart, you connect the diagrams together, and you end up with, you know, something that can be translated into running code. That's something, you know, flow-based programming, graphical flow-based programming that we're actually still working on and exploring today. So if you compare this and you know, the time at which this was done with the with what was out there in the world, like batch processing, you know, Unix computers and mainframe computers with teletypes, it's really a completely different world, right? And that's the key point here that I wanted to get across. We have a link in the slides here if you want to check out the video online, but we also have uploaded, in case you've got trouble watching these videos, we've uploaded the videos as a package for you to download from our internal repositories. Okay, next up we have NLS, the online system. And this is probably the most, maybe even more influential demonstration of a new system than Sketchpad. Sketchpad certainly, you know, takes its claim as the first sort of general purpose graphical user interface. But NLS, designed by Doug Engelbart and presented here in 1968 at a conference, featured not just a textual word processing system, but it featured a system that actually introduced a couple of new things that we're using today even. The key advances here, first of all, we're going to see a mouse. Engelbart, as part of his work here, introduces the mouse as a concept to computing. He introduces the concept of windows, not graphically overlapping ones, they're still tiled, but we're going to see multiple windows onto the same text here. We're going to see hyperlinking in action between documents. We're actually going to see, because, you know, why not, video conferencing. He'll be talking to a colleague over a telephone, over a TV conference, and they will actually be doing collaborative editing on the same document with two mouse pointers on the same screen. You will see revision control, so you can go through earlier versions of a document. As I said, various outlining and word processing features are there. This is really an incredibly impressive system. Engelbart really set out to try to augment the human intellect. You know, he was basically assuming, just like the steam engine had led to the Industrial Revolution because it was augmenting the human physical powers, he wanted to make it clear and explore how the computer could be used as sort of the steam engine of the intellectual age, if you want, augmenting the human intellect. And this was really sort of the kickoff for the whole PC revolution, because a lot of the techniques you'll see here then, you know, quickly made it into graphical user interfaces that could run on PC style hardware. So, but of course, Engelbart himself himself said that he was heavily influenced by, Sage, for example, for its real-time interaction. He was inspired by, how early punch card systems worked, and especially by the mimics, right? This was one of the visions that Engelbart found highly inspiring himself. If you want to find this demo, all you need to Google for is mother of all demos. This is such a wonderful demonstration of the system because he actually explains this system for the first time to a wide audience, not by holding a PowerPoint presentation about it or something. Well, there was no PowerPoint, but not just by showing slides or something, but actually by using the system itself through the whole talk and showing everybody what it's doing. And he talks about it, he uses it at the same time, he's using a bimanual interface here. As you can see, he's actually holding a 3-button mouse here in his right hand. This is a standard computer keyboard in the middle. And the left side here has a funky 5-button chording keyboard for pressing down with multiple fingers at the same time. Very interesting bimanual interaction here. And the way, some people have criticized Engelbart's design for being very complicated to learn. You'll see he actually uses some complex multi-finger inputs here that are hard to do, but he was interviewed and asked about this, and he said, well, you can have a computer that's easy to learn, and it's like a bike, it's easy, but you don't stick to the bike because it doesn't take you that far. That's not the only means of transport. So his vision was that if you learn complex technology, then it'll enhance your capabilities even more, and that's the more important thing to do. You augment the human intellect. So it was really focusing on expert performance, not initial ease of use, and in user tests of people who were not prepared to use it and hadn't gone through a training program and the learning curve of it, it failed because it was very complex to use. Some people were joking that it's perfect for a trained user who had 4 hands. But as I said, mother of all demos is what you want to Google for. Okay, so let's look at this this really inspiring demo, and also at I think a master of explaining his technology in a casual way with a real world task. He will actually talk about a couple things. He will make a little shopping list, and he will show you how he creates that shopping list in a folding hierarchical editor with headlines and subheadlines and all that kind of outlining technology. He'll show you how he then also goes through some documentation. He brings up a graphical picture of a mouse and how that's linked to his main text. And then there'll be a part that goes into collaborative video editing, collaborative editing via video conferencing. So that was a lot of stuff, right? What we saw in here was, first of all, of course, hyperlinks and hierarchical editing, with the mouse being used to actually mark up parts of the text. Even though the system didn't look very graphical at all, it was mostly displaying text. It had the ability to render some vector graphics. We saw that with the sketch of the mouse as well, and the route that he was following to go home with his shopping. But the input on it, like using the mouse on that screen, meant that you could go to any point on that screen and interact with it and mark things up just as you're used to today, using your mouse on your desktop. So when you pick up a mouse next time, Doug Engelbart is the guy who gave it the name. And did anybody notice something peculiar about the mouse, by the way? The mouse they were using, there was something that was significantly different from what you're probably used to. And I don't mean the metal wheels at the bottom. Victor.
The direction of the wire that was at some point like downside.
Yeah, exactly. So his original mouse was wired with a wire coming out towards you, which actually kind of makes it look even more like a mouse if you think about it, with the little buttons at the top and the wire at the bottom facing you. Exactly.
But it was weird because at some point of presentation it was from top, at some point it was from the bottom, so I'm not sure about whether it's a real client presentation completely.
Oh, the presentation is real. What you may see is pictures of different versions of it.
Okay.
I'll actually show you a picture in a second of the mouse in a little more detail. The listings, the hierarchical listing and the hyperlinking to other documents that you saw, you clicked on something, and then in the second window he opened up basically the target of that link if you want. There were split windows, for example, to get, in the front you had, top you had the text, and at the bottom you could see the definition of individual words from that text. Or, you could say what we saw there was basically Zoom 1.0, sharing a document and editing it together, kind of like a Google Docs thing plus video conferencing Zoom call. So, and again, remember this was, this was a demo from 1968, right? So, easily 50 years old. Quite impressive stuff, and shows that there are really brilliant folks out there in research that have these ideas way ahead of their time, and sometimes it takes a long time to really catch on for everybody to use, and some things just end up in everybody's everyday lives, and others don't. Here's the first mouse that Engelbart built a few years before, in 1964. With two wheels. The wire is still on the back, so pointing towards you, and it only had one button, whereas the one that he was showing there, I think already had 3 buttons, if I saw that correctly. These pictures, by the way, were taken by myself when I met Engelbart during a presentation at Stanford when I was working there as faculty. And he basically, this was like an early mouse encounters kind of historical meeting where he brought this stuff along and talked about it. The one button was just a design for a user test, and it also, if you actually use it, I moved it around a bit. The two wheels don't actually scroll smoothly, right? The one will scrape across the table, the other one will be rolling. But the tests that they did were, they asked people to put their hands on the keyboard. Then they had like an array of 3x3 objects, so 9 objects appear on the screen, and then the user had to press the space bar and then grab the pointing device and click on each object, right? And they tried this with the light pen, tracking ball, foot pedal, knee-operated device, head-operated device, and this was just the fastest thing out there. Okay, so from this really revolutionary system, both the sketchpad and Engelbart's first mouse, we're going to move into a more sort of hobbyist or back to sort of the mainstream industry things happening at the time. So we're now at the late 60s, early 70s, and how did the new way of interacting with computers, how did that transition into what people had access to at home? Well, first of all, they didn't have access to computers at home at all, because obviously computers had so far been only something that you could use if you were a government institution or a big business or like, an industry or a research lab. So computers were really not something that people had any access to in their private lives, or that they would encounter in their daily lives. And one of the things that happened quite early on were 2 things. First of all, Pong was invented. The first sort of computer game that really reached a bigger scale. There were others out there that had been available commercially before, but Pong was the one that made the big run. The first Pong console being constructed by Bushnell was really a huge hit on its first day. Basically, it was put up in a bar in Silicon Valley, and there was a line around the block before long for people who wanted to play this game. It turned out that it actually broke after a few days, and when Bushnell came by to check what was going on, he found out that it was one of the most beautiful bugs that you can possibly have, because what had happened was that so many people had thrown quarters into it that, you know, it was from like a laundromat, like a laundry machine, coin operated thing. It had filled up with quarters so high that the quarters had touched the bottom of the circuit board and were shorting out the circuit to run it. So he just had to empty basically the coins out, and then the machine worked again. I love when you can fix things that way. So what was the key thing here? Really, Pong was just using discrete circuitry, right? This was not a computer in the classical sense. It was really lots and lots of logic board circuitry that was creating this video game with some simple controllers on it and a black and white screen. Of course, they basically just a TV put in their TV monitor. But both this and the home computers that started to come out really started to give people a feel for what computers could do in their everyday lives. The Altair was the first computer that came out. Here's a little ad from the Popular Electronics magazine, the world's first mini computer kit to rival commercial models, the Altair 8800. And you could buy this, right? And if you bought the Altair, it actually came as a kit. You had to basically assemble it at home. Its user interface, if we talk about the user interface, was basically this row of LEDs there at the top, and below that there were rows of switches that you could use to program it, right? To put code into it. There was even a game that came with this. The game was something like this. You would flip a switch, and then the computer would light up an LED. And if you had flipped the right switch that the computer picked as the LED lit up, then you win. So it was not super exciting, but it was something you could put into your home, and basically it was just there really for people who wanted to play with computers because of computers, right? There wasn't anything useful you could do with this thing. Later on, actually, the Altair got expanded to 8 kilobytes of RAM, and you could even run a BASIC on it, written by a young student called Bill Gates. The Altair cost about $400 back then. It had 256 bytes of memory, so not terabytes, gigabytes, kilobytes, bytes. And the name, supposedly, the Altair, came from the episode that was running on Star Trek that week on TV, because that was the planet that Star Trek was traveling to on that very week when the name was being looked for. So you could say this is really a hobbyist thing that you cannot do anything useful with, but the personal computer came shortly afterwards, right? The first personal computer that was successfully introduced to the market was being introduced by Apple. The Apple II was the first one that actually was successful. The Apple I was a hacker device that basically was similar to the Altair. You built your own case. It had similar functionality, but it was basically a kit that you had to assemble. It didn't even come with its own box. You had to build your own box for it. So the Apple II was the first one that you could buy ready-made. This was the first general purpose personal computer that was widely used in business. And it came, why did it get used widely in business? Because of the software of it, of course. It was not the computer itself. It was really the software VisiCalc, which we'll talk about in a second, essentially an early ancestor of Excel and spreadsheets. Shortly after that, 4 years after that, IBM released the IBM personal computer, the IBM PC. Technically, it wasn't really much different from what the Apple II was doing, but the big difference here was that it made the concept of personal computers respectable to business in general by putting the IBM label on. Because IBM, International Business Machines, had been making large, calculator machines and large mainframes and so on for decades, for businesses, for insurance companies, et cetera, et cetera. So big business, really. And IBM, sticking the label on it and saying this is a PC, built by IBM, suddenly gave a whole lot more people the idea that this could really be a proper business device to use. Whereas the Apple II was used widely by small, businesses and corporations, but Apple wasn't a company at that time that people could take as seriously. I mean, they introduced their first computer and priced it at $666 just because it was the number of the devil, right? So they weren't really taking things that seriously. Both of these, with the Apple II and then later the IBM PC, featured, first of all, still a character terminal, meaning that you still had a 40 by 20 or later 80 by 40 character screen. It basically started slowly to evolve into standards. There were standards released for textual user interfaces. For example, IBM CUA, the Common User Access Guidelines, gave you the idea of how to design a text user interface to make it useful. If these things were able to display graphics, which they could, there were games for the Apple II, of course, it was not really standardized. There was not a standardized GUI, or none of these things had a mouse to come with, right? They were purely keyboard-based machines. I mentioned VisiCalc, and there's a really interesting short report on VisiCalc in a book called Bringing Design to Software by Terry Winograd from Stanford, where he talks about the inventor of VisiCalc. And VisiCalc is surprising because it's a software that was designed in the 70s. But it was a completely new genre of software. Nobody had worked with numbers or data in that way before. And that's really the exciting thing if you think about it. This was the first time that anybody came up with this idea of putting numbers in rows and columns on a computer and letting you compute certain cell values based on other cell values, add up things in rows and columns. So all of a sudden you had basically a live spreadsheet in front of you that as the business owner, you could use to make predictions, right? You could say, oh, if I change, the rate of the price for my product here, how does it affect, overall, returns or income over the year? And research, of course, similarly, this was a completely new way of thinking and being able to work with data. Nobody had been able to do that. So it was a new mental model for users, but people picked it up very quickly because it was such a useful and appropriate model to work with numbers. Of course, they had seen ledgers before on paper to work with numbers, but it was, it was this, electronic version of it that was dynamic and that you could use to do what-if scenarios, right? And you can see here, it's actually pretty standardized from today's point of view, right? You basically have a field up there where you enter, where you can edit what the current line contains, the edit line, and you've got, your rows, 1 to 20 here. You've got columns A and B. Then you can see actually there's a separate window being opened here, showing rows K and L. So we can look at two windows in split screen style. We've got a cursor highlighting a particular row and column or a cell here currently. We already have ways to format things as dollars and cents for finances. We can format things right justified, left justified. We can have labels that repeat themselves. We even have a graph output, right? You can output things as graph by putting little stars next to each other to indicate a rough bar chart, right? Different formats like integer, etc. Value entries, formula entries, and so on and so on. So it really feels a lot like what you know today from Excel. But we're still on the industrial side, at least, of things. We are still firmly rooted in the text interface, right? We're still working with 80 by or 40 by 25 cells of characters on our screens. So the ideas that we saw in NLS by Engelbart had not made it into any commercial devices yet, but that was about to change with the introduction of bitmap displays and graphical user interfaces. The first system that introduced those concepts to a commercial device, not a research prototype like Sketchpad, the NLS, was actually the Xerox Alto. It was developed by PARC. PARC was a research facility, and still is, that was run by Xerox at the time. And a lot of the things that we today take for granted in computing were invented at that place. The Ethernet was developed at PARC. The laser printer was developed at PARC. Wi-Fi was invented at PARC. So PARC was really the growing place and the origin of a lot of modern computing technology. The Alto similarly started at PARC as a product that Xerox wanted to push to revolutionize how the office works, right? How people work in the office. So you can see an example of the computer here. What you'll notice is the screen is actually portrait mode, right? That's an interesting way, because they were really thinking of, let's replicate, the printed page, right? That's the idea. So that's why you have a format like this for your display and not landscape. We can see the chording keyword is still there, so that made it over from Doug Engelbart. Also, the mouse, more importantly, is there. It now, I think, has 3 buttons, if I'm not mistaken, on this one. The way that this thing was hardware-wise equipped was, it had a removable hard disk. That was actually before floppies were introduced. It had a removable hard disk with 2.5 megabytes of storage, and you could get it with up to 256K of RAM, 600 by 800 screen resolution, the mouse, Ethernet, but it was never actually, it never turned into a commercial product because it was revamped into the Star, which we'll talk about next. How did the software run on this? This was actually running under Smalltalk. Smalltalk being an object-oriented language, very powerful, very open, and everything on there, from the operating system to the GUI to the applications running on it, everything was written in Smalltalk. It was a completely homogeneous software system. We'll talk more about this in DIS2 next semester when we look at the technology and the software infrastructure that these people built to handle events and process these things and create graphics and widgets and all that stuff. We'll talk about more about that in the next semester. The editor on there was the Bravo editor as a text editor, it was actually, it actually turned into Word later. So for a long time, you still found parts of the Bravo original code in Word as a software package. It offered the possibility to do email. The resolution of 600 by 800 of that screen was actually astonishing for given that time. At the time, this was unheard of, because remember, before we'd only seen character screens, or maybe that really ugly vector style drawing that the early Sketchpad could do. So the idea of splitting the screen up into pixels, in these tiny pixels, and being able to address every single one of them individually was completely unheard of before, right? That was completely new. So the bitmap display that let you do black and white pixels originally, no grayscale, no color, that came later. And with that, the real graphical user interface that had windows being outlined, a mouse cursor that you could move around, being able to point to things, drag windows across the screen, drag objects across the screen, drag something into a folder, etc. All of these things, as we now know them, were introduced by Xerox with the Alto. One of the main advocates of the Alto and the Smalltalk platform was Alan Kay, who was working at PARC back then. He had an idea, a vision of what he called the Dynabook, which was actually more like a laptop or an iPad that he was imagining people ultimately to own and sit under a tree and use. And this was sort of the first sort of implementation of leading towards that idea. This also, by the way, the Alto and Xerox at that time coined the term personal computer, although this system never saw the personal use because it stayed in the lab and wasn't commercialized. 8 years later, which sounds like a really long time, and it kind of is, certainly from today's point of view, but 8 years later, the Xerox Star was complete. The Star was the follow-up to the Alto that actually introduced the whole idea of a graphical user interface with windows and mouse pointers, etc., commercially. You could buy it for about $17,000 in 1981. That's a lot of money in today's currency. The key advances of this was, above the Alto, which of course it was built on, was it had an integrated network document environment. So you could actually work in a work group and see file servers on it, you know, from other people and share files that way. It offered you what you see is what you get text editor, WYSIWYG. And that was something that nobody had actually seen before. Even when we take a look at, you know, what we saw with the demo by Engelbart, he was clicking on individual letters, but it was all just, you know, unformatted text, right? You couldn't see anything in like boldface or italics or anything like that. The Star also introduced the idea of having icons on your desktop, having what they called property sheets, which were kind of like dialogues where you could do settings on a particular object. It introduced the idea of window management so that you could arrange and lay out windows in different ways. So it was really designed to improve a lot over the Alto. What I find exciting about the Star is not just that it essentially then became the first commercially available graphical user interface computer. Notice I'm saying commercially available, not commercially successful, right? But it was also a very unique design process that the team went through. I worked with one of the designers when I was at Stanford who had worked on this team of people who designed the graphical user interface, and he was a graphic artist. And he said that it was really a highly iterative process to find the best icons for everything. They introduced this whole idea of talking to users when they were designing this and really making users part of the design process. Nielsen would, you know, call this area of computing when we moved to the graphical user interface a 2.5D interface, which is kind of, don't take these dimensions too mathematically serious, right? It's more a way of lining these things up in a row. So when Nielsen says 2.5D interface, how he explains it, he says, well, it's a 2D interface like what we were able to do in a full text screen, but now we have overlapping windows, so we can actually start stacking things in at least mentally and conceptually for the user. There's a video about the Xerox Star, and this is something you should look at, and I find it really impressive how close this is already to what we're still doing today when we interact with the desktop. It's really surprising. And remember, nobody had seen a desktop, a mouse, well, they'd seen a mouse, but not on a graphical user interface with windows, with icons, the pointer being moved around to drag things around. So this was really being introduced by the Xerox Alto and the Xerox Star. So we're going to see a short video of the Star. All right. So a couple things that I thought are really remarkable here. First of all, I really want a big red stop button on my computer. I love that idea. I wonder why that's ever gone away. But you know, the buttons were, I think, an interesting part of this, and we're actually going to have a separate slide on that here. If you look at the keyboard, beyond the mouse and the standard keys, this button section here on the left had all these interesting, you know, dedicated hardware buttons to do common functions, like, you know, anything that had to do with editing here was on the left. anything with formatting was on the right, and then we have the top sort of typographical ones. If you take a look at these things, for example, the same button also worked in an interesting way, right? You first selected something that you wanted to format, and then you press same, and you said like to make that the same as this other thing. That's actually the exact reverse of how today's paintbrush works that Word uses, for example, to paint an existing style over another target object. So it's interesting to see how sometimes these metaphors also change, right? Why did they change at some point? Must have been some results from user studies that showed that the original didn't work well. The selection, for example, of text like single, double, triple, quadruple clicking is just what we know today, right? That seems like that code made it straight into Microsoft Word, for example. Not surprisingly, since we're still talking about the Bravo editor and its follow-ups here that led to Word ultimately. Some other things are strangely different, right? For example, the desktop, while it showed files and folders the way that we would expect them today, also showed, for example, an inbox, right? The email was so tightly integrated into the desktop that it was replicated as a physical inbox right on the desktop. You could open it and it would immediately open a window. It didn't seem like you were now in an app that was doing mail, right? It was more like, yeah, well, that's my email inbox, and why should that be any different from my stack of papers next to my email inbox? That's an interesting trend that we've been seeing going back and forth, by the way. There's been big movement into document-centered computing, where basically OpenDoc, for example, was an initiative that tried to make sure that people just have to work on documents. They don't have to think about apps at all, because apps are an unnatural sort of split of I'm really working on documents, and if it contains a spreadsheet, I'm going to insert a spreadsheet, but I don't want to use a different app for that. And nowadays, especially with what we've seen happening on the mobile space, we are actually working in a highly app-centric environment, which makes working on compound documents surprisingly difficult. So it's a back and forth, I think, that we're seeing in that particular connection. You also notice probably that this was a really slow system, right? So it took forever to render that page of what you see is what you get, previewed text. But that shows that it was still running with a Smalltalk system underneath, and that was not known for its performance. It was extremely flexible, extremely powerful, but not very fast. Also because there was cooperative multitasking going on, so it wasn't a system that was able to easily prioritize certain things much more highly than others. And of course, the hardware was also just simply slow, right? The system was a bit ahead of its time because it was trying to do things that in principle worked, but were really slow to use in everyday tasks. Something else that I thought was really striking, did anybody notice this about the file names that you could use on files on the in the system? He said a few things about the way that you could name files when you were putting them in there. Yeah, Jasper, go ahead.
Yeah, they don't have to be unique, so only the timestamp was there to differentiate.
Yeah, and wouldn't that, doesn't that freak you out as a computer scientist? Like, oh my God, a file without a unique name. Oh my God, how is that going to work? Blah, blah, blah. But I like this as an example because it shows that on my actual physical desk, I can have 2 copies of the exact same document, and I probably want to have a little mark on one that says this is the current one, this is the last one, but why look for different names for them, right? This is really something that we as computer scientists take for granted, that of course files in a folder on a computer have to be, in a directory, have to be different, otherwise how are you going to tell them apart? But they don't have to be, right? If you think about how humans work, you might say, that's actually not necessary. It's more a technical requirement that we've today, for example, mostly moved into the computing world. So people would never try put 2 identically named files into the same folder. And in fact, it doesn't work today. But it's really more a limitation that is born out of the technological sense of Unix file systems and stuff like that. What I thought was interesting also is that when he popped up the property sheet for printing, the option sheet, he explicitly said, this instead of having to remember all the options for this command, you can just pick them here. Remember, what people used to see until they saw this demo was that you would call a command by typing in its name on, for example, like, an IBM PC or an Apple II or one of those home computers, or even on a time-sharing system, right, on an IBM mainframe. You would type in a command, you would add all the options, from your memory, or you'd have to look them up somewhere, and then you would send off the command, right? So you had to specify. Command line interfaces always require you to memorize and type, whereas the graphical user interface lets you see, read, and select from what's there, what's offered to you. So when you think back to Norman's principles of visibility and ease of learning and ease of use, of course, the graphical user interface has a huge leg up in the competition because it shows me the options that are available to me, the commands that are available, the arguments that I can add to a command like printing. They're just visible to me and I can pick from them. I don't need to learn them by heart and then type them in, make mistakes, mistype them, etc. All that gets removed with the graphical user interface. At the same time, it makes things slower, of course. Renaming 15 files by adding a .old to them, for example, is faster in a command line interface rather than doing it in a graphical UI. And I just love when he says things like, oh, we call this the desktop, right? Or we call this selecting text, or this is called a window. This is a time where people just hadn't seen this stuff. And you can see this is when these concepts were really introduced to a wide audience that we're taking for granted today. There was also an explicit help key in the hardware, which I thought was interesting to see. Of course, the hardware keys that those are no longer around today, right? We don't have these keys anymore. What has replaced them instead? Yeah, Victor?
We have shortcuts.
We have shortcuts, exactly, right. And if you think about it, again, from a visibility point of view, shortcuts are okay, but to find out about a shortcut, you actually need to open the menu and look at the shortcut if it's given to you there, right? So it's not quite as visible as this dedicated hardware key, but we can also see that the Star and the Alto were designed really as office machines, right? These are all the useful things, like, you have a dedicated button for italics on your keyboard, right? Very single purpose, which makes that task, of course, really easy, but it makes it also less flexible, right? This would not be a machine that you could easily use in a completely different task, like, movie editing or something. The buttons up there would make very little sense, so they would be kind of wasted on you, and you might want different buttons up there instead. So it's this continuous struggle between, am I staying more task focused and make a more dedicated device, or am I going to go for a more universal design? Here's the set of buttons that had to do with formatting that were all on the right-hand side with the keyboard, font, margins, etc. Also the help button, and like I said, my personal favorite, the stop button. I want that on my keyboard. The Star, we have a reading assignment for you on the Star, not to go into all the technical details on how it works, that's not that critical, but how the team around the Star derived at principles of how to design good user interfaces, because this was a key part of what Star left as a legacy. It left a new way, a new process of how to design software and hardware. The principles that are taken from that paper that you'll have as a reading assignment are to really go through a design process first before starting to code, that refers to the fact that they really try to get their iconography right, their conceptual models right before they started to build all this stuff. They introduced the object and action concept, meaning on a GUI, that's another key difference here. On a GUI, you typically first pick an object, for example, a file, and then you do something to it. For example, you duplicate it or you pull it on the printer, right? So select an object, then issue an action on it. Whereas in a command line interface, you're going first with the action, and then the object, right? You first say delete, and then you enter the file name of the file to delete. If you do action object in a graphical user interface, you create a mode, and modes are bad, right? Because they are one of those, they create mode errors, as we know. I mentioned the way to where some early Windows system allowed you to turn your cursor into a skull, which meant the next window you click on will be killed without asking you, next app will be killed without asking you for any confirmation. If you, then get a phone call, you get distracted, and you come back and you just click on a window to select it, and you didn't pay attention to your cursor, boom, you killed an app that contained some important document. So that's a mode error, and you don't get those if you first have people select an object and then have them trigger the action on it, because selecting the object doesn't break stuff. And when you select the action, you're paying attention to the action and at that very moment, and so the mode error is much less likely. They just also paid a lot of attention to detail in the graphical user interface. For example, going through dozens of iterations on the individual icons for how do you visualize a document? How do you visualize a folder? How do you visualize a file server, et cetera, et cetera. They work with graphic designers, which was also new in the industry. So far, all these interfaces were basically text-based. So why hire a graphic designer where all we're doing is show text, right? So that was a new way. And finally, they introduced what we'll get to know as the DIA cycle. That's my name that I give it. It stands for design, implement, and analyze. It's this iteration over, you have an idea, you design something, you create a prototype, and then you evaluate it, you test it with users, without users. There are various ways that you'll learn. And then you go back to the drawing board and you improve your design. So this DIA cycle, as we call it in this class, is probably the most fundamental principle in user-centered design, right? Other people call it task artifact cycle or iterative design cycle or whatever you want. The agile movement is also closely related to that from an implementation point of view. So all this sounds great. So why didn't the star actually hit the market and become a huge success? Well, first of all, the industry at the time that the star was released, late 70s, early 80s, was heading for the PC, right? The PC hit the market IBM PC hit the market in 1981, and that was just what the industry was going for. The second problem was that it had a focus on the office environment, because that's what Xerox really knew, right? Xerox makes photocopiers, right? And that was their business. So they really knew the paper-based office and wanted to create a power workhorse for that environment. But this was not going to be useful to many, many other people who wanted to do different things with their computers. One way that particularly shows this is that the original design of the star was actually not intended to have additional software being installed, right? This was a system that was supposed to be done as it is, with the set of applications running on it and not adding any additional applications. And so that ultimately really narrowed down its applicability to office work, where it was really a great design, right? Responsibility was bad. As I said, the hardware was just not ready. Let's say the complexity of the software, as elegant as it was built at a too high abstraction level, requiring too many translation steps down to the silicon to run on the the CPUs that were available at the time. And finally, the desktop metaphor started, even when they are already running, at least in the way that was done on the start, it started running into certain limitations. It was, at some point the metaphor was breaking down for what people were trying to do with it, especially with these dedicated keys that were very sort of office task centered. And finally, it's also just hard to sell radical innovation, right? This was completely different from how people were used to work. They had maybe seen an Apple II and maybe seen how you do work on a document there with WordStar, that an early version of a word processor on PCs. And this was very different, right? The mouse was new for people. The graphical user interface was new to them. It's hard to sell this kind of radical innovation unless you really get the whole package completely right for people. So it was very different from what people had seen so far, and the business world was, a little hesitant to jump into that. So because the star didn't succeed, that doesn't mean that it didn't have an impact, because what happened was that Apple, with its Apple II on the market, was, these guys are all sitting in Silicon Valley, they're living next to each other, right? So Steve Jobs visited PARC in 1979 after the Alto had been done and the star was almost finished. And he saw what they were doing with the Alto, what they had done with the Alto, and what they were doing with the star. So he decided to pick up that idea of a graphic user interface. He immediately saw the incredibly improved usability potential here. He took up this idea and created what's known as the Lisa. The Lisa was actually Apple's first bitmapped graphic user interface computer. Looked like what you see here on the right-hand side. We now have the mouse down to one button, something that Apple has been holding on to for a long time. In part because studies at the time showed that people not used to a mouse were struggling with, was it the left or the right mouse button that I'm supposed to click? And it was largely a design inspired by the Alto, not the star quite yet. What was it that the Apple Lisa did differently? Well, it ran on a Motorola 68K processor at 5 megahertz, so 68,000 processor. It introduced, for example, the menu bar, the fixed menu bar that sticks at the top. And as we know by now, instead of what the Alto was doing, the pop-up menus all over the place. And that, of course, meant that you could now always go up there, throw the mouse up against the top of the screen and find your menu there. It also helped people to feel safer because they always knew where they would find all the commands that they needed to look at. It gave people a grounding place, a safe place to go to for reference for what to do and which application is currently running and so on. One reason of that is because a menu bar never disappears. It takes up screen real estate, but it's always there. So you always go to it, you always see it. Context menus are invisible. So if you forget about them, then they're not there, right? They're not easy to discover. Just like, gesture-based interfaces are incredibly hard to discover if you don't know about them. Other than that, it ran much on the same principles of the desktop environment here, but the problem was it was still too slow. It was very underpowered. Also, the marketing point wasn't quite right. It still cost around $10,000, which was better than the what the star was going to sell for. But it was still a price beyond the average business, small business. So and it was underpowered. It was too slow. That Motorola chip was not able to crunch through that code on the Lisa fast enough. So there were lots of jokes out there. The knock knock jokes, right? Knock knock, who's there? And then you say something, and the joke around the Lisa went like, knock knock, who's there? And then you leave like a 50-second pause, and then you say, Lisa, because it was so slow. The last Lisas, so Lisa was not a commercial success. The last Lisas were actually buried, and I mean that literally buried, in a landfill in Utah, in Logan, in 1989. This was because Apple, was needing a tax write-off at the time to get rid of that old hardware. So not a successful, not a success commercially. We can still take a quick peek at the UI here as the last slide here. This is the final user interface of the Lisa. So it already looks a lot like the Mac interface did then that came later. You got overlapping windows, you got a menu bar at the top, you got a scroll bar on the right and on the bottom. You got, this is running Mac Paint, for example, bitmap graphic editing. We'll talk about more about this in DIS2. It already made use of a library called QuickDraw that we'll talk about when we get to the Mac next week. I think I'll stop here in the interest of time. We will have a little bit on how the Lisa is another example of ideas resurfacing after many years. But for now, I'd like to close here today and hope to see you all again next week for the remainder of our little trip down memory lane and looking at both the past and also visions of the future. Thanks very much for listening, and see you again next time.
This content was provided by RWTH Aachen University.